Today, we're going to trace the incredible, high-speed journey a single thought or feeling takes as it zips through the crazy, complex wiring of your brain. From a simple idea to a powerful emotion, it's all part of the same amazing biological process.
I mean, seriously, have you ever thought about it? It feels instant, right? But behind that incredible speed is this remarkably precise bioelectric dance. So let's break down exactly how your brain sends that message from point A to point B. All right, first things first. Before any message can be sent, you need the infrastructure. You need the roads, the wiring. Let's meet the hardware of your own personal information highway. Okay, think of this as our cast of characters. The star of the show is the neuron. That's the cell doing all the talking. It listens for signals with its branch-like dendrites, and then it sends its own message down this long cable called an axon. Now, to make that signal super fast, the axon is often wrapped in this fatty insulator called the myelin sheath. At the very end, you have the terminal buttons, which release chemicals across a tiny, tiny gap called the synapse. It's a seriously efficient setup. So, we've got the hardware. But how does the message actually travel? Well, it's not some gentle, continuous stream. It's a single, powerful spark, an electrical impulse. You know, a neuron basically has two modes, ready and fire. When it's in its ready state, that's called resting potential. It's inactive, but it's holding this stable negative charge, just waiting. When it gets the right trigger, boom, it unleashes an action potential. That's the fire moment. It's this brief, dramatic flimp in its electrical charge that sends a wave of electricity shooting down the axon. And here's the cool part. It's an all-or-nothing event. It either fires with full force or it doesn't fire at all. There's no in-between, which keeps the message perfectly clear. And check this out. Resting doesn't mean it's at zero. It means it's holding steady at precisely -70 millivolts. That negative charge is absolutely crucial. It's like a compressed spring, packed with potential energy, just waiting for that one little trigger to be released. And once it fires, the neuron can't just fire again immediately. It has to take a very short break. It enters this mandatory cool-down phase, the absolute refractory period. This is so important because it makes sure that signals are clean, distinct, and only travel in one direction. It's the system's way of hitting the reset button before the next message comes through. Okay, so our electrical spark has just raced down the axon at incredible speed. But now it hits a problem, a big one. There's a physical gap, the synaptic cleft. Electricity can't just jump across CUM. So, now what? How does the message keep going? This is where things get really clever, because the signal switches from being electrical to being chemical. So when that electrical impulse hits the end of the line, it triggers the release of these tiny chemical messengers called neurotransmitters. They literally float across that microscopic gap and then lock onto receptors on the next neuron, kind of like a key fitting perfectly into a lock. That click delivers the signal and tells the next cell what it needs to do. It's this beautiful, elegant chemical handshake. So the message has been delivered across the gap, but what does the message actually say? Well, you might be surprised at how simple it is. It really boils down to one of two commands: go or stop. And this is what that looks like. The chemical message creates a tiny voltage change. If it's an excitatory PSP, it's a positive jolt, making the next neuron more likely to fire. That's the go signal. But if it's an inhibitory PSP, it's a negative shift, making it less likely to fire. That's the stop signal. It's kind of wild to think that all of your most complex thoughts and feelings are built from billions of these simple go and stop messages. So, who are these chemical messengers? I bet you've heard of some of these. Acetylcholine is what tells your muscles to actually move. Dopamine, that's the famous pleasure and reward signal. Serotonin is all about mood and relaxation. Norepinephrine gets you revved up for a stress response. GABA is the main stop signal that helps reduce anxiety. And, of course, endorphins, your body's amazing natural painkillers. These tiny little molecules have a massive, massive impact on how we feel and experience everything. Now, after the message is sent, you can't just leave all those chemicals floating around in the gap. The brain is way too efficient for that. It has this brilliant cleanup and recycling program called reuptake. The original neuron just sucks the leftover messengers back up, clearing the way for the next signal. It's one of the key reasons our thoughts can move so incredibly fast. So now that we get how this elegant system is supposed to work, we can also see how it can be influenced or, hacked. Lots of things, from your morning coffee to prescription medications, work by getting involved in this exact process.
And there are basically two ways they can do this. An agonist is a substance that perfectly mimics a natural neurotransmitter. Think of it like a copy of the key. It fits in the lock, turns it, and opens the door by activating the receptor. An antagonist, on the other hand, does the opposite. It's like a key that fits in the lock but then breaks off. It just sits there, blocking the door so the real neurotransmitter can't get in and deliver its message.
All of this leaves us with a pretty fascinating and kind of mind-bending question. We've seen that everything from a simple muscle twitch to a feeling of pure joy is really the result of this precise electrochemical dance, a cascade of signals and chemical handshakes. So if our entire experience of the world is built on these carefully timed chemical codes, what does that say about how much control we really have over our own minds? It's definitely something to think about.